Let me put some stuff on the board that's going to be of use today. I think you guys got all this on the board on Friday, right? When we were doing the acceleration of gravity stuff. So it's all the same stuff. One of these numbers is wrong. And I didn't do it intentionally, but that should be 1.49 times 10 to the 11th, not 1.47. It doesn't make that big a difference, but it means that when you calculate the period that it takes for the Earth to go around the sun, you get the wrong answer. You get 355 days, not 365 days. So we'll correct it and make sure we have the right answer. Okay, I want to talk about ratio problems first. And do you remember last Friday? I know it was a long time ago. We were calculating like the acceleration of gravity. We did how we showed how to calculate the acceleration of gravity. I want to just go through it real quick to remind you what we did. And let's say that we wanted to find the acceleration of gravity on Mars. And that was the one I gave you to do when you were leaving. I said, well, you just want to take somebody and drop them really close to the surface of Mars so that they are accelerating towards Mars. That would mean that they are experiencing an unbalanced force, with this acceleration being the acceleration due to gravity, because it would be the only thing acting on them would be the force of gravity. And then we said, well, that unbalanced force would be Newton's law of universal gravitation. So if we were talking about dropping U near the surface of Mars, that would be the mass of Mars, the mass of U, G, and the separation distance between you and Mars, which, if you're near the surface, means the radius of Mars. And that'll be equal to the thing being dropped, the mass of U, and G. Guys, remember this on Friday? And then we just canceled out the mass of U, and it left you with the acceleration of gravity. And this is how you calculate the acceleration of gravity on other planets. You just need the mass and the radius. And we did that for the Earth, and we all got 9.8 meters per second squared. Okay, so I want to show you a type of question that often gets asked. And you might think this is what you're supposed to do. But it's deceptive, because they'll ask this question without giving you masses and radii to use, which might mean like, well, am I supposed to memorize that stuff? Or worse, they do give it to you and you go to do the problem and it takes you too long. So let me show you what this other class of problems sounds like. It'll sound like this. New planet is twice the mass of the Earth, but 3 times the radius. They want to know the acceleration of gravity on the new planet. Now, you could do this problem by grabbing the mass of the Earth and doubling it and getting the radius of the Earth and tripling it, and that would work. But that's not the intent. They chose the Earth on purpose. They chose the Earth because they hope that you know that this all equals 9.8 meters per second squared, right? And then they made a problem around a planet that is proportional to the Earth, 2 times the mass and 3 times the radius. So I want to show you how they're expecting you to solve this question. Okay, they are not expecting you to get the mass of the Earth and the radius of the Earth. Here's what they're expecting you to do. They're expecting you to say, okay, my new planet, it is 2 times the mass of the Earth and 3 times the radius of the Earth. They want you to take the numbers and put them into the function like this. Then, and this part's tough, they want you to separate the numbers from the symbols. So I'm going to take the 2 and the 3 and I'm going to separate them. I'm going to pull them to the left and I'm going to collect all the symbols to the right. So this is going to be 2 with M, E, and G over there. And then this is going to be 3 squared with RE squared over there. You see what I've done? See how I've taken the numbers out and collected the constants again. The reason is because everything that's in here is equal to 9.8. we're collecting the stuff that we know equals 9.8 on purpose so that we can replace all of this with just 9.8. This is a ratio problem. They want you to figure out what the ratio change is. They don't expect you to recalculate it. And they'll put this on like multiple choice and stuff like that very frequently, because it's something that you can do rather quickly without having to use a whole bunch of like prior knowledge. You don't need to know the mass of the Earth. You don't need to know the radius of the Earth. You just need to know the function that describes the said variable. You guys follow this okay? There's 2 or 3 versions of this question. So how about we try another example just like this one to see if you've kind of got this one down, okay? So I'm just going to change the problem up here a little bit. Let's say it has half the mass of the Earth and we'll say half of the radius of the Earth. Okay. What is the new acceleration of gravity on our new planet? All right, can you try that one? The answer is 19.6 meters per second squared. So see if you can do this one. I'll give you a second. All right, so did everybody do the same thing I'm doing? I'm going to put 1/2 mass of the Earth times g over 1/2 radius of the Earth squared. Is that what you guys did? So I'm going to take the 1/2 out. I'm going to take the other 1/2 out, and I'll get 1/2 over 1/2 squared times and then we just work that left side out, which I find to be 2, right? 1/2 divided by 1/4 is 2. So 2 times 9.8, which is 19.6. You did know that 1/2 divided by 1/4 is 2, right? It's okay. How'd you do it?
I multiply 9.8 by just 0.5, which I got 4.9, and then this is 1/2 squared is 0.25, and then I just divided 4.9 from 0.25.
That is exactly the right way to do it too. That'll work just fine. So proud. All right. So not so bad. This is pretty easy. One more. Just one more. I'm going to on purpose. So try that one. 2 objects have a mutual force of attraction due to gravity of 20 newtons. What is the new force if you double the separation distance? And I'll point out, we don't know the mass of either object, and we don't know the separation distance. So just 2 random objects are feeling a force of attraction of 20 newtons when they are this far apart. If I double the separation distance, what is the new force of attraction? Okay, you have to know which formula we're dealing with here. Do you guys know which formula we're dealing with? Okay, so this is going to be the one we talked about on Friday, Newton's law of universal gravitation. We know that because it says their mutual force of attraction due to gravity. And we know that this equals 20 newtons. Now that's what we're starting with, but we're going to go through and follow the same process. Did M1 change? Did they change the value of M1? Did they double the mass or anything? Read the question. Did any of the masses change? Doesn't look like it, so I'll write M1, M2, G. Did the separation distance change? By how much? So I'm going to put 2r squared. I'm going to separate out the numbers from the letters. So there's no numbers to separate out on top, so I'll just put a 1. But on the bottom, it's 2 squared. And that gives me m1, m2g over r squared. Except all of this is how much? 20. So 20 divided by 4, or 5 newtons. You guys feel pretty okay with this stuff? These are the easy ones. All right. Okay. Am I good to... Now, here's what I really want to talk to you about today. We're going to talk about 2 things about orbits. We're going to talk about generic orbits, and then we're going to talk about circular orbits specifically. So I want to talk about generic orbits first, but an orbit is a repeated path that an object takes around some kind of central object. For today's discussion, so I don't have to say orbiting object and central object, I'm going to use planet and star. Is that okay? So that's my example today. I'll use planet and star. But understand, this could be a moon and a planet. This could be a spaceship and a planet. It could be anything that can orbit something else. So I'm going to say that we're dealing with a planet and a star today, and then we'll do a different example as well so you can see 2 different examples, okay? Generic orbits, as described by Kepler, because this is one of Kepler's 3 laws. Generic orbits are elliptical. And I don't know what your understanding is of ellipses from your math class. So I'm going to not assume very much. So every piece of vocabulary I'm giving you is the vocabulary I need you to know for my class, but you may need to know more when you finally encounter this in pre-calc. So an ellipse has several different ways of being measured, but for us, we're going to talk about two important details, the semi-major and semi-minor axis. The semi-major axis is the long one, and the semi-minor axis is the narrow one. So when we talk about an ellipse, this is the minor axis, this is the major axis. But an ellipse is just a squished circle. And we describe how squished it is by something called its eccentricity. We use an E here, but I'm not gonna write eccentricity because I'm afraid I can't spell it. So it's just gonna be like an E. And it's the ratio of the minor axis to the major axis. And you don't need to know much about this. What you do need to know is that the smaller this number is, the more squished your ellipse is. But the biggest this number can be is 1. And 1 is a circle. So an eccentricity of 1 means the minor axis and the major axis are the same size, and that means a circle. However, as long as you have an ellipse, ellipses don't have a center necessarily. I mean, they do. They have a spot here in the middle. But they have a more important measurement called the focus. And ellipses have 2 focal points. You'll learn to calculate that in pre-calc. But you'll notice I put an X on one and a dot on the other. Because when we talk about orbits, the star is always at one of the focal points. Remember, our example today right now is planet and star. So the star is at one of the focal points, and the planet is traveling around the ellipse. Generic orbits are elliptical, with a star at a focus. Kepler's first law. Now, he has other laws too, but we don't have to worry about them today. What I do want you to know is that this orbit is not particularly special. The fact that it's an ellipse makes it more complicated, so we don't talk much about the mathematics here. But you should know that when the planet is all the way far away, I think it's called, I don't even know what the name is. It's aphelion or something like that. But I forget how to spell it and say it. So when it's at its farthest point away, it's traveling the slowest and has the weakest amount of gravity acting on it because the separation distance is biggest. And as it travels from the farthest point away, it speeds up the whole time until it makes it to its closest point. At its closest point, it's traveling the fastest, but has the strongest force of gravity on it. Of course, as it travels away from this point, it's slowing down. So anything in elliptical orbits is always speeding up or slowing down. And it has a maximum speed here and a minimum speed here. Now, there is more to know about elliptical orbits, but not much more for us for this unit. I will say most planets have an eccentricity that is nearly 1, which means most planets are in circular orbit. So we're going to study circular orbits because elliptical orbits may be complicated, but circular orbits have some simplifications. So let's consider a circular orbit. In fact, we'll consider the Earth's orbit around the sun, which is nearly circular. Right out the gate, one of the things I hope you understand is that when you have a circular orbit, the semi-major and semi-minor axis are the same. We just call that a radius now. So a planet that's in a circular orbit is always the same distance away from the star. Which also means that a planet that's in circular motion is always traveling with the same speed. It's not speeding up or slowing down. It's traveling with the same speed all the time. It's also experiencing the same force of gravity all the time because the separation distance isn't changing. So it experiences the same force of gravity. Now that force of gravity is always towards the sun, which makes it a center-seeking force. So, and this is the most important part of today, an object in a circular orbit is experiencing an unbalanced force that causes centripetal acceleration. An object in a circular orbit is experiencing an unbalanced force that causes centripetal acceleration. So, to calculate an orbit, which is what I want you to be able to do, you will need 3 things. You'll need Newton's law of gravity. You'll need the definition of centripetal acceleration. And you'll need something we talked about weeks ago but tends to get forgotten all the time. You'll need to know that if you're traveling at a constant speed, velocity is distance over time. Those 3 things should look familiar to you. They're on the board already anyways, so I put them on the board over there. But you're going to combine these 3 things to figure out orbits. It's always the same combination of things. For us today, we're going to do 2 things. We're going to figure out how fast the Earth is going, and then we're going to figure out how long it takes the Earth to go around the sun. And we know the answer. It's 365 days. So a lot of these, we will know the answer ahead of time. But we're going to practice, and I want to show you where it comes from. All right, you guys ready to go? Let's start with this. It's a Newton's second law problem, and the force involved is gravity. So let's handle the first part, the gravity part. This has 3 features: the mass of the first object, the mass of the second object, and their separation distance. So let's put it all together. The first object is the sun. The second object, the Earth. G is just a constant, and R represents the separation distance. That's what we're going to start with. So this is the force that is acting on the Earth. It's also the same force that's acting on the sun, but the sun's really big, so the Earth is the thing that's changing. This has to equal ma. But before we go any further, which m do we put on the right side? And I'm, again, not trying to trick you. The m on the right side is the thing that's going in the circle. So what's the thing that's going in the circle? The Earth. So we're going to put the mass of the Earth here. Good job. All right, so that's step 1. We put in our Newton's law of universal gravitation into our formula, and we make sure we put the correct thing on the other side, the thing that's going around the orbit. Step 2, we're going to substitute in for centripetal acceleration. Okay, we're going to substitute in for centripetal acceleration. Now, I want to stop here real quick and call something to your attention. You'll notice I'm using different R's here. Are you noticing? That's not accidental. This R, I've said it out loud several times, is separation distance. This R and this R is radius of curvature. For the most part in this class, we're always going to have situations where the radius of curvature and the separation distance are the same. But you should know they don't have to be. The radius of curvature and the separation distance are the same if the thing in the middle is really big compared to the thing that's orbiting. That's when they're the same. But if the thing in the middle isn't really big compared to the thing that's orbiting, you have to do something different. You have to use the center of mass. Now, we're not going to do that yet. We're going to do that in our next unit. So for this unit, these two R's are going to be the same. And it works for this one because the sun is so much bigger than the Earth. But believe it or not, it doesn't really work for the Earth and Moon. The Earth and Moon are actually pretty close in mass. So to get the right answer for the Earth and Moon, you do have to correct. But we're going to assume today that we're okay getting the slightly wronger answer. And we'll do the Earth and Moon as if the Earth is much greater than the Moon. Okay? Because that's going to be our second example. So I want you to always stop, though, and ask, is the radius of curvature the same as the separation distance? And if so, make them both the same R. If not, they have to be separate R's. Okay, do you notice things cancel here? I'm noticing things cancel. The mass of the Earth cancels. And because we said the separation distance and the radius are the same, one of the R's cancels, giving me mass of sun, G over R equals VT squared. Okay, step 1. It's kind of all the way done now. I'm sorry, this is our part 1, not step 1. Part 1, we're done. We found the velocity. I said there's 2 things you have to find for orbits. One of them is the velocity of the thing that's orbiting. We are here. So take a second, grab your calculator, and tell me that the velocity of the Earth is 30,000 meters. You need the practice. So see if I'm right. You should get that VT equals, I got 29,846.7 meters per second. You guys getting the same thing? I hope so. It takes a little practice sometimes with the big numbers. Do you need me to help you at all? All right, we feel good about this, okay? All right, this is part 1. Part 1 is getting the velocity. Okay? I want to do part 2 now. Part 2 is using the velocity to figure out the period, how long it takes. This one's a little harder because the answer you're going to get is in seconds, and you want to convert it to something that makes sense. And what is it? You already know the answer. How long does it take the Earth to go around the sun?
24 hours.
But it doesn't take 24 hours. How long does it actually take? There you go. So we probably want to put our answer in days and don't leave it in seconds. Does that make sense? And we'll be able to prove that it's not 24 hours, which will be good too. So the second part involves us recognizing that the velocity is equal to 2 pi r. We've already shown that this isn't the radius of this is the radius of curvature and the separation distance, so I'm putting the capital R there, over t. We want t, the period. So first thing, we'll solve that for t, and we'll get 2 pi r divided by the velocity. All right. See what you get. You don't get 365, by the way. You're going to get something close, but not 365. So, if you do it right, you should get like 363 days. Now, part of the reason we're not getting closer to 365, which we should get closer, is one of the numbers that's up here is a little inaccurate on purpose to make sure you get this number. And sometimes they'll do that. They'll put slight inaccuracies on there so that they get a specific wrong answer, so that you don't just guess and put 365. So, and we're also using numbers that have been rounded a little bit, and that's also making it so we're not getting the exact right number that we would expect. But we won't get 365 anyways because of leap year, because we know that it's not perfectly broken up. Go ahead.
How do we convert seconds to days?
That's okay. I'm glad you asked because I know 4 people in 6th period who couldn't do it but wouldn't ask. So they just walked out of here with the wrong answer. So let's talk about how I would do it. I would use unit multipliers personally, and that's what I just did here. Meaning I would say start by doing one conversion at a time. So remember that this is a single number, so I'm just going to put a 1 under here. And I want to get rid of seconds and be left in minutes. That's one conversion I can make. And I have a conversion fact for that, right? 60 seconds for every 1 minute. And then that's not quite going to be good enough, so we're going to have to do it again. This time probably go into hours. But I'll cancel the minutes, be left in hours. Again, I know you know the conversion fact, 1 hour is 60 minutes. And then hours won't be good enough. We'll need to go to days. So and so 24 hours for 1 day. So basically, you're just dividing by 60, and dividing by 24. And that'll get you your 363 days. But this time, do the problem trying to figure out the period of the moon around the Earth. You should get 27 days. So moon around the Earth starts with net force equals ma. So mass of the Earth, mass of the moon, g over r squared. And which mass do we put here, moon or Earth? Moon, that's the thing going in the circle, that's right. Times AC. So that's a good start, right? Now, we can cancel out the mass of the moon. But we'll have to put in there VT squared over R. Again, you should ask yourself if the radius of curvature and the separation distance are the same. They actually aren't for the Earth, but we're going to act like they are. That allows us to cancel out one of the R's. And this is what you have to do to get the velocity.